Hello everyone, welcome to the last math club talk of this semester. Today we have Adrija Chatterjee with us, and she's interested in probability theory and statistics, and today she's going to present on iterated function system in approximating fractal dimensions. So over to Adrija.
Thank you. So here we'll be talking about a system of functions called iterated function systems, and we'll also be talking about different notions of dimension because it's not a very clear concept, especially for special sets like fractals. So firstly, you guys know about the Cantor set, right? So what is a fractal? When, say for example, the Cantor set, so you keep on zooming into it and the set keeps on repeating itself at all scales. However much you zoom in, the set keeps on halving and halving and halving, and you see the same set over and over again. So that is a property called self-similarity. And well, a Cantor set is a fractal. I won't be able to provide a very precise definition of fractals here because it requires a lot of measure theory and all to understand. But I'll be going over it, and also I'll define two specific notions, which are the box dimension and the Hausdorff dimension, because I want to talk about how they can be approximated properly using iterative function systems. So, well, this is a 3D fractal generated, and the size of this picture is 114 MB. So fractals are found in many places in nature. You will be seeing them everywhere. So, well, the first one is a fern, then it's a broccoli, then it's a pine cone, that's a snowflake, that's a blood vessel, that's a lightning shock, and then you have a river network, you have foam, you have that coastline, that is the cloud cover before cyclone. That is a succulent, and that is a tree bark. So in all these places you will see fractal nature. So firstly, okay, so I'll start with the theory of it. So all of you know what a contraction is, right? So it is defined on a closed set, and all the fractals we'll work with over here are compact sets, so it's fine. So we have a contraction here. Then, so what is an iterative function system? It is a finite collection of contractions, and this is an iterative function system can be defined on contractions. But firstly, we will be starting with contracting similarities, which is exactly like Sx minus Sy is exactly equal to C times x minus y. So it's just a scaling of the original image, and then we will move on to the general contraction. Okay. So, do you guys know the Banach fixed point theorem? Okay, so basically you have a contraction on a set in Rn, say, and say a contraction T. So an invariant point is a point x such that T of x equal to x. Okay. So Banach fixed point theorem says that there will always exist a unique fixed point for such a complete metric space, and Rn is complete, so it's fine. So, well, since it's an invariant point, and we are working, instead of just one map, we have a set of maps over here. So we can talk about an invariant set, right? We can generalize it to a set. So you have an IFS S, and the attractor of that IFS F is basically the invariant set of that function system. So it satisfies F equal to union Si of F. And as you can see, if you iterate F over and over again, the original fractal doesn't change. So it's basically made of scaled copies of itself. So F will have a sort of fractal nature, because say in the previous example in Cantor set, the more you zoomed in, the sets just kept on halving. So it's a contraction, and you keep on doing it. So that is the fractal. For the next part, this is a definition you have to know for the next topic. So Hausdorff metric is basically the minimum distance. So Hausdorff metric is a metric defined on two sets, and it is the minimum distance R such that set A lies in the rth boundary of set B, and set B lies in the rth boundary of set A. So this is your set A, this is your set B. So if you take R to be this and you take this, then A is a subset of the rth boundary of B, B is a subset of the rth boundary of A, and similarly if you take this and you take this, then A is a subset of the rth boundary of B. So you take the maximum of those two, and that is the Hausdorff metric. And for this theorem, this is the next theorem we'll talk about, the iterated function theorem. So the theorem is basically that there will always exist a unique attractor.
How do you define the rth boundary mathematically?
Oh, it's basically just this set. So take all points of set B and take the rth ball, and then take the union of those balls.
So like a ball of mathematics.
Yes. And for you do that for all points of set B, and you will get the rth boundary of B. Okay. So this is the iterated function theorem, and you have a set of functions IFS. So what this says is that there will always exist a unique attractor to any IFS. Like just like Banach fixed point theorem, the invariant point was unique. This is also unique, and the proof is basically an application of Banach fixed point theorem, but you are defining the set to be all compact subsets of your original set. So instead of defining T from X to X, you are defining T from compact subsets of X to compact subsets of X. And the metric you are considering is the Hausdorff metric. So there will exist an unique attractor, and the attractor will be given by, so you will take any set E which satisfies Si of E is a subset of E for all I. So whichever map you apply, whichever map of the IFS you apply to E, the image will always stay inside E, it will not escape E. So if E satisfies this condition, then the attractor can be computed by taking the intersection overall Sk of E, where okay, so S1 of E is basically say your IFS consists of those maps S1 to Sm. So the first iteration will be S1 of E union S2 of E union ... union Sm of E. In the second iteration, you will take S1 of S1, S1 of S2 up to S1 of Sm, then S2 of Sm, S2 of S2, S2 of S3. So you will take all the compositions. So at the kth level, you will take all the k-fold compositions of your S, and then you will get the attractor by taking the limit as k tends to infinity. Okay, so this is a lot of theory, and let's see.
So when you are writing S per k of E, shouldn't that be S per k of I of E?
Oh, S power k of E is defined to be this. So S of E is defined to be union Si of E.
So but we are defining both as F.
Huh? F?
So like when you take I as 1,
Huh.
okay, like the first iteration. So you take every one power, then you define F. No, wait. Okay, sorry.
It's fine, right? So basically the first iteration is just the union of the images. The second iteration is the union of two-fold composition. Then you keep on taking the k-fold compositions, and then you take the intersection. So this is basically how you generate fractals online. So you keep on applying the maps on a set, and well, R will only approximate it because you can't take tends to infinity over there. You will take a very high value, and then you will keep on repeating the iterations over and over again, and that's how R will approximate your fractal. And however, obviously this is a very complex problem in terms of time and space. So there is another way to generate such a fractal. So the first one I talked about is deterministic iteration. So you keep on iterating ek plus 1 equal to union Si of ek, and you will get your fractal. The other method of computing the attractor is you take any point belonging to the set, you choose any map of the IFS randomly and uniformly, and you apply it to that point. So say you have x, you start with x0, and the first map you take is say S2. You choose S2, you pick up S2 out of the set. So your next point will be S2 of x0. So now you have x0 and S2 of x0. Then you will again pick, say this time you pick S4 out of the set of functions you have. So then your next point will be S4 of S2 of x0. So you keep on applying random functions to the most recent point, and the total union of those points will approximate the fractal. And since instead of applying all the maps, you are just choosing one map randomly and applying one map, it is a much easier problem. Okay, so now we will come to the examples. So Cantor set is an attractor because wait, I'll erase the word. So first you start with your 0, 1, then you apply the first map x by 3. So 0, 1 will basically shorten to 0, 1 by 3, and then you apply the map x by 3 plus 2 by 3. So now this 0, 1 will first shorten down to 0, 1 by 3, and then it will shift by 2 by 3. So basically the image is 2 by 3, and then you take the union of these two sets and you get the next iteration. And this is the first iteration of your Cantor set, and then you will repeat this again. So here you will apply, actually I have it drawn here. So here you will apply this, wait, x by 3. So your 0, 1 by 3 will first become 0, 1 by 9. Then your 0, 1 by 3 will first shorten to 0, 1 by 9, and then it will shift by 2 by 3 to give you 2 by 3, 7 by 9. Then you will first you will shift it. So first first I applied the iterations to this set. Now I will apply the iterations to this set. So here when you shorten it, you go back to 2 by 9, 1 by 3, and then you shorten it and then you again shift it, so it maps to 8 by 9, 1. So then you keep on repeating this for all the sets here at each iteration, and the limiting set will be your Cantor set. So then you have the Sierpiński carpet, where how is it generated? First you start with a square of like 1, 1 size, then you divide it into 9 small subsquares and you remove the middle square out of it. So now you have 8 subsquares. You repeat this for each of the 8 subsquares. Basically you divide them again into 9 parts, and then you again remove the middle parts out of it, and you have the second iteration. So you keep on doing this and it will tend to your Sierpiński carpet. So what can the functions be? So first you have this square. So in order to shorten this square into this small square here, you will basically take x by 3, y by 3. Then you will shift it here by x by 3 plus 1 by 3, y by 3. That will lead to the second square. Then you will shift to this square. So x by 3 plus 2 by 3, y by 3. And you apply those 8 functions like this over here, and this square will basically map to your 8 subsquares. And then you repeat the same functions for this, and this each of those small squares will again map to the further subsquares. So these are the contraction maps, x by 3 plus t of I, where ti belongs to this set. So you are basically removing the middle square, so you are removing your 1 by 3, 1 by 3. Okay, so this is the Sierpiński carpet generated on R. And this has been done using the second method. So I choose a random point, I choose a random function, and I apply the random function to the random point, and then you get the next point. So repeating this for I think 10,000 steps gave me this thing. Okay, and then you have the Sierpiński gasket. So same thing kind of. So you start with, instead of the square, you start with the triangle. You divide your triangle into 4 sub-triangles, and then you remove the inverted triangle from the middle. Then again you divide each of these 3 triangles into the further sub-triangles, and then you remove the center pieces. So now the contraction ratio here is 1/2, because see, this has side length 1 and this has side length half. So your map, so when you want to map this triangle into this small triangle, you will just take x/2 comma y/2. Then here you will take x/2 comma here you will take x/2 comma y/2, and then you will shift it by half, so this triangle reaches here. So the maps here look like this: x/2 plus ti, where ti can be 0 comma 0, basically the lower triangle. Then it will be half comma 0, so the lower right triangle, and then you will have 1/4 comma √3/4 to take it to the top. And the Sierpiński gasket is the unique attractor of this function system, and again this is generated on R using the same way. Okay, so now I will come to the concept of dimensions. So there can be, I will only go over 2 types of dimensions here, the box dimension and the Hausdorff dimension, because that's all I've dealt with using iterative function systems. So first you have a bounded set F, and you take boxes of size epsilon, and then you try to cover your set with those boxes. So let the minimum number of boxes of size epsilon required to cover your set be n of epsilon. Okay, then your box dimension will be limit epsilon tends to 0 log of n of epsilon by log of 1 by epsilon. So this is basically the definition, and I will give you examples. Also, when this limit does not exist, you have the concepts of upper box dimension and lower box dimension. So basically the lim sup of this and the lim inf of this. So first, very easy example, this is 0 comma 1 whole square. So first you have the 1 cross 1 square, and epsilon is 1. So basically this set itself is a box of length 1, right? So 1 box is enough. So n of epsilon will be 1. Next you have epsilon 1/2. So now you have boxes of size 1/2 cross 1/2. So you will need 4 such boxes to cover your original set. So your n of half will be 4. So you keep on doing this, and when your epsilon is 1/2 power n, you will require 2 power 2n boxes to cover your original set. So when you compute it, it's basically log of n of 1/2 power n by log of 2 power n. So that will equal to 2. So obviously your box 0 comma 1 will have dimension 2, that's what we know, and this, so the box dimension matches for it. Next I'll go to the fractal Sierpiński carpet. So it's very similar, because it's basically just the boxes, but you keep on removing the central boxes from it. So first again it's the same thing, you have epsilon equal to 1, and in order to cover the first iteration of it, which is just the box, you will require only 1 set. Next you will have 8 subsquares of length 1/3 cross 1/3. So when epsilon will be 1/3, you will need 8 boxes to cover this figure. Then when epsilon will be 1/9, you will require 8 square boxes to cover this figure. So similarly at the nth iteration, when your epsilon is 1/3 power n, then you will need 8 power n boxes to cover your original figure, and you can do this by comparing the areas as well. So the area of the whole set divided by the area of a single box. So your limit is basically log 8 base 3, and so the dimension of your Sierpiński carpet is log 8 base 3, which is around 1.89, I think. So as you can see, it is like a square but not quite a square, because its dimension is very close to 2, but it is not exactly equal to 2, and this is where we encounter fractal dimensions for the first time. Also, yeah, for the Sierpiński, sorry, for the Cantor set, your dimension is around, I think, 0.63. So your Cantor set is a subset of a line, obviously, line 0, 1. So its dimension will be less than 1, less than equal to 1. And however, it is, we know that the Cantor set is totally disconnected. So it is basically, it's more like a set of points, but it is an uncountable set of points. So we can't say that it has dimension 0, just like a point. So it makes sense that the dimension of a Cantor set will be somewhere between 0 and 1. So it's around 0.63 if I am not wrong. And this is the second fractal dimension, which is around 1.89. And similarly for the triangle, your dimension is log 3 base 2 in the same way. So previously we had to cover 8 squares with boxes of size.
How do we find the Cantor set dimension? That was my question.
Oh, exactly in this way. So this is a more complicated case of this Cantor set basically. So okay, so I'll show it to you. So in Cantor set, you first start with a line, right? And your box in R is basically a line segment. So when your epsilon is basically equal to 1, then you need one line segment to cover this set. When your epsilon is half, then when your epsilon is 1 by 3, then you will need 2 sets to cover this thing. Then when your epsilon is 1 by 9, again it gets divided. So you will need 4 sets to, so this will be covered by one set, this will be covered by one set, this and this. So you will need 4 sets to cover with epsilon equal to 1 by 9. So when epsilon equal to 1 by 3 power n, you need 2 power n sets to cover it inductively. So you're applying that formula, your dimension will be log 2 power n by minus log, it will basically be log 3 power n. So which is your log 3 base 2. Is it okay? So for the triangle, previously we covered 8 power n squares with boxes of side length 3 power minus n. Now we are covering now we are covering 3 power n triangles, because at each step the number of triangles keeps on getting multiplied by 3. So you are covering 3 power n triangles with boxes of side length 2 power minus n. So it's basically the inverse of the Cantor set, where you covered 2 power n, where you covered using 2 power n sets when epsilon was 1 by 3 power n. So it was exactly the opposite. So your dimension here is log 3 base 2, which is around 1.58. So it's not as 2-dimensional as the Sierpiński carpet, but it's not 1-dimensional either, because it's more than 1 dimension clearly. Okay. So the next dimension is again very theoretic. So I won't go very deep into it, but I'll just go over it because it's necessary for the next part.
Yeah, is it ever possible that the box dimension overshadows the topological dimension?
Yes, so basically a fractal is when, so okay, if you know what a topological dimension is, then a fractal is basically a set whose box dimension is strictly greater than the topological dimension. The topological dimension of this set is 1, the topological dimension of this set is also 1. Huh?
The topological dimension of this is 2, right?
No, it's 1. For that you need to know the definition. It's there in my report if you want to refer to it. It's a very long proof. It's a very long proof. But yes, the topological dimension of this is 1, the topological dimension of this is also 1, and the topological dimension of the Cantor set is 0. Basically a set is disconnected, totally disconnected if and only if its topological dimension is 0. So now we have the Hausdorff dimension. Okay. So first we have to define a measure for it. So the S Hausdorff dimension of a set is basically you try to minimize. So you are given the restriction that for some delta the diameter of each set has to be lesser than delta. So then you try to cover your set with such sets of diameter less than delta, and then you try to minimize this value, summation diameter of ui power s, and when you take the lim inf as delta tends to 0, that value gives you your Sth Hausdorff measured. So this is just the formula, and basically the Hausdorff dimension is the set is the value for which the Hausdorff measure jumps from infinity to 0. So yes, basically this is what the Hausdorff measure looks like for a particular set. So it starts off with infinity unless, okay, so if the Hausdorff dimension of a set is 0, then it's basically constant 0 throughout the real line or throughout S. Otherwise it starts off at infinity, at a point it randomly jumps down to 0 with a point of discontinuity in between, and then it's constant all over this. And well, I do have a proof for this, but I won't go into the proof as it's not very relevant to the topic. But so this dimension D at which there is a point of discontinuity is the Hausdorff dimension of a set. Okay. So now say you have the attractor of a set of an IFS. So F will be equal to union SI of F for the attractor, because that's the definition of an attractor. Say all the functions of the IFS are contractions with are similarities with ratio Ci. So your Hausdorff dimension of F will be summation of Hausdorff dimension of SI of F if the union there is disjoint. So measure adds up when the union is disjoint. So, and obviously the Hausdorff dimension of SI of F will be equal to Ci power S of Hs of F because of scaling. So when you scale a measure, it scales by, so say you scale a set by S, so the Hausdorff measure of that set will also scale by S. So here it's scaling by Ci power S. So your Hausdorff measure of SI of F will be Ci power S of Hs of F. So basically your Hausdorff dimension of Hausdorff measure of F will be equal to summation Hausdorff measure of Hs of F. When you cancel these two out, you get summation Ci power S equal to 1, and that S gives you your Hausdorff dimension. So the main point is that this is how you can easily calculate the Hausdorff dimension of an IFS with contracting similarities. So this may not always work, but we will talk about this set called this condition called open set condition. So originally what did we assume here? In order for this to be exactly additive, we need the union here to be disjoint, right? But the union may not always be disjoint. So there must be a condition that is enough for this condition to hold, and that is the open set condition. So if a fractal, if an attractor satisfies the open set condition, then we can say that this is equal to this, and hence we can easily compute the Hausdorff dimension of that set. So open set condition is basically when if there exists a non-empty bounded open set such that the image lies inside the set, so union Si of u is a subset of u and the union is disjoint. So for example, okay, no, example will come later. So you have the IFS here, and so this is basically the theorem I talked about. Say it satisfies the open set condition, then the solution to summation Ci power s equal to 1 will give you your Hausdorff dimension, and that will be equal to the box dimension. So this is a pretty strong theorem, and that will and this tells us that when your iterative functions are all of similarity, like all the functions in your IFS are basically similarities, then your Hausdorff dimension and your box dimensions are equal, and this is how you compute it. So yes, so what about when it's not a similarity but just a contraction? So it's a contraction if your modulo Si of x minus Si of y is less than equal to Ci of x minus y. So in that case, you can say that this S will give you an upper bound for your Hausdorff dimension and upper box dimension. So you can't say that the dimensions are exactly equal to S, but you can say that the dimensions are less than equal to S, where S satisfies this thing. So this gives you an upper bound. So we also need and if we can get a lower bound for this too, then it will be very easy to approximate the dimension of a set, even when its IFS is not only similarities but general contractions. So we gave an upper bound. Similarly, the lower bound is very intuitive actually. So it was originally less than equal to Ci of x minus y, but what if it's greater than equal to Bi of x minus y? So it's bounded below by Bi of x minus y. In that case, summation Bi power s equal to 1, the solution to this will give you your lower bound for the Hausdorff dimension, and also the added fact is f is totally disconnected. So you can now bound your thing, your set, with both S1 and S2, where S1 is the solution to summation Bi power S1 equal to 1, and S2 is the solution to summation Ci power S2 equal to 1. And first we'll start with the normal examples, Cantor set, Sierpiński carpet and Sierpiński gasket, because they are just similarities, so you can just apply the formula to get the dimension. So if you remember, in Cantor set, you keep on dividing the intervals, so you keep on dividing the intervals into 1/3 of the original length. So your similarity ratio is 1/3, and you are getting 2 sets per iteration, so your C1 and C2 both are 1/3. So your Hausdorff dimension and box dimension both will be equal to the solution to this 1/3 power d plus 1/3 power d equal to 1, which is basically when d is around 0.631. So log 2 base 3. Next you have the Sierpiński carpet, when you have, now you are dividing your square into 8 subsquares, right? And all of these subsquares have length 1/3 of the original length. So now your contracting similarity is ratio is 1/3, and the number of sets you are getting at each iteration is basically 8. So you have 8 times 1/3 power d equal to 1 given the previous formula, and your d is coming out to be 1.893. So log 8 base 3. Similarity for Sierpiński gasket, you can get log 3 base 2, because you are getting 3 triangles of half the length. So your similarity ratio is 1/2, and you are getting 3 triangles. So 3 times 1/2 power d equal to 1, so d equal to log 3 base 2, which is around 1.585. Okay. So now we have an example here which is not a similarity, but it is a contraction. Basically the map is a contraction, as you can see, 1 plus 1 by x and 2 plus 1 by x. So does anyone have any questions before this? Okay. Okay, so firstly what the theorem says is that you have a set and you keep on applying the transformations 1 plus 1 by x and 2 plus 1 by x on this set D, which is an interval, and this implies that the dimensions will be bounded by 0.44 and 0.66. We already saw a way of bounding the dimensions by a lower dimension and an upper dimension, which was given by summation bi power s equal to 1 and summation ci power s equal to 1. So we try to do that here. So originally, see that S1, it's visible, right? So S1 of D, when you apply this S1 to D, then it is equal to 1 plus root 3 by 2 comma root 3, and S2 of D is equal to 3 plus root 3 by 2 comma 1 plus root 3. So these are so the open set condition holds here because these are disjoint sets. So now we will want to bound these transformations by some contracting ratio. So we need C such that say we are working with S1 first, S1 of x minus S1 of y is less than equal to C times x minus y for all x and y. So we need to find a C for that, and we also need to find a B which bounds it in the other direction. So B times x minus y is less than equal to this. So how do we find this B and C? Or like you can divide this entire thing by mod of x minus y, and then you will get something similar to mean value theorem. So you divide this thing by x minus y, so by mean value theorem we know that for all x comma y there will exist a z such that this will be equal to mod of S1 derivative at z. There will exist a z such that this will hold. So this will be bounded by B and C. So it is enough to find the minimum of this value and the maximum of this value. So what is your S1 dash of z? Actually your since it's just constants, your S1 dash of z and S2 dash of z are basically equal, and it is equal to minus 1 by z square because it's 1 plus 1 by x and 2 plus 1 by x. So mod of that will be so mod of Si, because it's the same for 1 and 2. So mod of Si dash of z is equal to 1 by z square. So now applying this thing, we can find that it will be bounded by 2 minus root 3 by 2 and 2 times 2 minus root 3. So the minimum of this value is basically, we needed B, right? So your B turns out to be 2 minus root 3 by 2, and your C turns out to be 2 times 2 minus root 3, because you basically compute the maximum of this value over your D and the minimum of this value over your D. Okay, so now applying the Yes, so applying this theorem, we know that it will be bounded by your summation, the solution to summation bi power s equal to 1 and summation ci power s equal to 1. So here this is your b and this is your c, and this will give us our first bounds, which is basically from here you will get that the dimension of this set is bounded by 0.34 and 1.11. Okay, and now this set D is a subset of the real line, so the dimension of D will obviously be less than equal to 1. So we figured out that, wait, I need to erase the word, there is no space. We figured out that 0.34 is less than equal to dimension of D is less than equal to 1.11. However, we already know that the dimension of this is less than equal to 1. So we need to do better. So we need to make these bounds more proper. So originally we tried to minimize the value of si dash of z, right? Now we will try to minimize the value of si of sj dash of z, because if f is an attractor of s1 and s2, then f is also an attractor of s1 of s1, s1 of s2, s2 of s1 and s2 of s2, because we take the iteration as k tends to we take the intersection as k tends to infinity anyways. So we take the, instead of taking the one-fold composition, now we take the two-fold compositions. So initially we calculated the bounds for this, now we try to calculate the bounds for this, and the value of this is equal to I plus 1 by j plus 1 by z, when I and j are equal to 1 and 2. Yes. So si of sj of z is equal to this. So when you try to compute the modulo of the derivative, you get j plus 1 by x power minus 2. So wait, I took z here, right? So now we try to bound this with a minimum and a maximum, and previously the minimum of this value was 2 plus root 3 by 2, I think. No, it was 2 minus root 3 by 2, and the maximum of this value was 2 times 2 minus root 3. But now on enhancing the bound, we know that we will get sharper bounds for this basically, and applying this to the 4 maps s1 of s1, s1 of s2, s2 of s1 and s2 of s2, we will get our bounds 0.44 and 0.66. So the second iteration will give you 0.44 and 0.66, and now you keep on taking the 3-fold iteration and the 4-fold iteration. So instead of taking, first you took si, then you took si of sj, then you will take si of sj of sk. So you will keep on repeating this, and you will see that this bound increases to 0.531 and this bound decreases to 0.531. So your dimension of this set is basically 0.531. Yes.
Is there any closed form representation of the derivative of the k-fold iteration?
That you have to calculate. Given this, you have to calculate. It's already the second. So for the second iteration, your si of sj is equal to I plus 1 by j plus 1 by x, and then you apply that, and you will get your next iteration.
Okay, so I mean this dimension, is it calculated analytically or it is generated by simulations?
The dimension?
the Hausdorff division of F.
You can do both. I am pretty sure this is theoretical. This can be verified analytically, yes. Basically, you can try this. It's a very dirty calculation, but you can try this. You can keep on applying the iterations and taking the derivatives and bounding it both sides by your S1 and S2, and you will get this bound. And this is how the nonlinear Cantor set looks like on a graph. So it's one dimensional, so basically the set itself is just the projection of this on the x-axis, but it's non-linear because the this part, so a lot of points fall on this part and this part, then this point, this part and this part, the yellow parts are not reached at all. So when you try to map your iteration over and over again, you will see that this part and this part are the densest parts, and this part and this part are the least dense parts. Okay, so for the last topic we will try to talk about self-affine sets. So previously we talked about contractions. Now for each of the sets we considered all the coordinates had the same contraction ratio. For example, in the triangle the contraction ratio was half. For the square, the Sierpiński carpet, the contraction ratio was 1/3. So both x and y were scaled by the same ratio. What if the x and y contractions are different? So the matrix has basically different eigenvalues and it is non-uniformly contracting. So this self-affine transformation is basically a transformation that will map your square to a parallelogram or a sphere to an ellipsoid by contracting different coordinates by different ratios. So self-affine set is basically an attractor of such an IFS. So say your IFS has self-affine transformations, and you take the attractor of that IFS, and that IFS will be termed a self-affine set, and that is also a fractal, but that is a generalization of the fractals we worked with before. So yes, a compact set F satisfying this is called self-affine. It is the invariant set under those transformations. And this is a very interesting example. So first I'll show you the picture. So take the first image at the beginning. So you have this square here, and you map this square to a rectangle, and that rectangle maps here, and then you map it into another rectangle, and that rectangle touches the sides of the square and it maps here. And then if you repeat it, so basically your 1 cross 1 square was mapped to half cross epsilon rectangle, both above and below but in different positions. And then you repeat this, and your set here maps into this. And so when you repeat this entire transformation for this one set, the first set will be mapped around here and the second will be mapped around here, and for that set as well the first set will be mapped around here and the second set will be mapped around here. So wait, I think I need to draw it. That one, actually I can just erase this. Okay, so first you had 1 cross 1 here, which got mapped into this rectangle and this rectangle of side half epsilon, and this is also half epsilon. Okay, now you will apply the same map to this set first. So what happened to this set is what will happen to this set now. So again there will be a rectangle here and a rectangle here of length 1 by 2 power 2 and epsilon power 2, and here it will be mapped to this and this. Then you again repeat this, so now you have these squares with you, so this one, this one, this one and this one, and then you repeat this entire transformation for these 4 squares, no, rectangles. So
different only for the first transformation. After that, they are basically similar because you are just making it.
no, you are applying the same transformation. So again, so
First
it will
convert 1 into half.
and 1 into epsilon.
1 as equals 0.
Huh?
You are taking 1 as half equals 0.
Yes. And then this will be mapped to this and this. This will be mapped to this and this. So you keep on getting windows. And if you keep on going like this, the ending set is your attractor F of the initial transformation. Now this gap is basically your lambda, and if you make, so basically what the theorem says is that if you keep on decreasing lambda for non-zero lambda and epsilon less than half, your Hausdorff dimension will always be greater than equal to 1. However, when lambda will be 0, your dimension will be equal to minus log 2 base epsilon, which is less than 1. So it is not a continuous function of lambda, given that when lambda is greater than 0, the dimension of this set is always going to be greater than equal to 1. As soon as this entire thing shifts here, the dimension is going to be less than 1. So this is the problem we face with affine transformations when we try to generalize our contractions or contracting similarities into these affine contractions. This is the problem we face. There is no proper way to compute these dimensions, and it is often just discontinuous. And for an idea of this proof, you can see that if you take the projection of all these on the x-axis, so let this be the x-axis, then you can see that the projection will be like this up till half. So it's from 0 to half, around here. Actually it depends on lambda. Wait, I will tell you the exact value.
So is this lambda the eigenvalue or it is just the distance?
It is the distance.
And it is the position of the upper rectangle or the lower rectangle?
Oh, I am taking the projection of the entire attractor. So basically what happens is, when you transform this set into these two rectangles, then the rest of the sets just gets vanished. And
You are doing that iteratively, right?
iteratively, yes.
At which point are you taking the projection?
So okay, so in the first iteration it was just this set. So the projection of this set on the x-axis was this entire set, entire line. In the next iteration, the projection is this line union this line, so it will be till here.
Union means the complete one, right?
From here, so you go from here. So what in the second iteration, what did you have? You only had these two rectangles, right? So the projection of this rectangle is still here, and the projection of this rectangle is still here. So
Half plus lambda.
yes, half plus lambda, yes. And then so the main point is that the projection of this figure is always a proper line segment. So when this gets shortened to these four small rectangles, then the projection of this will be till here, the projection of this will be till here, this will be till here, and this will be till here. So the entire union will be this line segment in the next iteration. So you keep on doing this and you will see that the projection will be this line segment, and if the projection of a set is a line segment, then obviously the dimension of the set has to be greater than equal to 1. So when lambda is greater than 0, the dimension will be greater than equal to 1. But now we will check the lambda equal to 0 case. I have to draw again. So now lambda equal to 0, so the first iteration will be here and here. Yes, okay, that's fine. Then the next iteration will be here, 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 here. So as you can see, now you take the y-axis instead of the x-axis. So initially the y-axis looked like this when it was the whole thing. Now the y-axis looks like this and this. After that it looks like this, 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 this. Any similarities to the Cantor set? Okay. So when you keep on iterating over and over again, the thickness of these tends to 0 because it's epsilon power k and epsilon is less than half. So they will tend to points, and basically it's like a Cantor set with your 1 minus 2 epsilon removed from the center at each stage. So the dimension of this will be your log 2 by minus log of epsilon, the box dimension, and that will be equal to the Hausdorff dimension. So the dimension of this set will be your log 2 by log 1 by epsilon, which is obviously less than 1 as epsilon is less than half. So we saw that the dimension is kind of discontinuous. And for the last example, I won't be proving this example as it's a very bad example. So basically I will show the picture first. So you start with a square, then you choose an integer, a natural number p and a natural number q such that p is less than q, and then you divide this entire rectangle into a p cross q subarray. So this gets divided into p cross q rectangles, and then you select rectangles randomly from your subarray. And then in this figure you repeat this process for each of the triangles remaining, and you choose the same triangles you chose in the beginning. So basically, should I draw this? Okay. So say your p equal to 3 and q equal to 6, just this example. So you have a p cross q subarray, so 3 cross 6. Now say you pick, which squares did we pick here? We picked this square, this square, this square, this square, this, and this one, right? So here is what we chose. We chose 8 squares here. 1, 2, 3, 4, 5, 6, 7, 8, yes. And now what is remaining of this set after the first iteration is these 8 rectangles. And now what you will do is you will repeat this process for each of those rectangles again. So I can't draw anymore. So for each of these rectangles you will choose the same 8 squares that you chose in the beginning, and you will do this for each of these rectangles, and this is what you will get as the next set. And you will keep on doing this over and over again, and the attractor of this system will be your set, the set that we are talking about. And what happens is, say your nj is the number of rectangles selected from the jth column. So here your n1 is 4, n2 is 1, and n3 is 3. So nj is defined that way, and your p1 is the number of columns containing at least one rectangle of this e1, so your set. So here all the 3 columns contain at least one rectangle. This one contains 4, this contains 1, this contains 3. So here your p1 is 3, n1 is 4, n2 is 1, and n3 is 3. So for given this information, you have your Hausdorff dimension to be this and your box dimension to be this, and this is one case where your Hausdorff dimension is not equal to your box dimension. So dimension of a set is basically not unique, it depends on which definition you are choosing. So yes, that is the thing, and this was the last example of my talk. So these are the references. Falconer has a very detailed analysis of whatever I taught here, so you can refer to it. And for more measure theory and real analysis, you can refer to Folland. And the last one is the report I made in my summer project with Shivatra, so you can refer to that as well. And thank you. Any questions?
Anyone has any doubts or questions regarding the talk? Okay, so let's thank the speaker once again.
That's it.